Okay, so today we're doing the Diels-Alder reaction. So with this, we're gonna have a diene, so a conjugated diene, and then a dienophile. And then so the reaction mechanism is a concerted reaction mechanism where you have the arrows all pushing in one way. So you have your diene attacking the dienophile, which then of course attacks the other side. And then you create 2 sigma bonds and 1 pi bond. So this is an interesting reaction because you get the translation of the stereochemistry from the diene. So here we have a from the dienophile. So you have a cis dienophile, and then so your product you generate is a cis product. And so with the Diels-Alder, it's kind of hard to see, but there's nothing stopping the attack of the dienophile from the top or from the bottom, so it's going to do both. And so generally you generate enantiomers, but when you have a cis product like this and no R groups on your diene, then you generate these 2 products which are the same product. So you convince yourself that these are the same product, you just take this, you flip it over, it's the exact same product, okay? And then so you can also have your attack from your dienophile with the R groups pointing in or the R groups pointing out. And so if we look over here, you see that, and this is also on page 8, you see that there's this, and sorry, it's kind of hard to see here, but there's this favored overlap between one of the p orbitals of your diene and a p orbital of the R group on your dienophile. So this favored overlap, you see it here and you see it here, prefers the endo product, which is kind of interesting because you would think sterically speaking the endo product should be disfavored, but almost all Diels-Alder reactions initially favor the endo product, and it has to do with this favored overlap here. However, with that being said, Diels-Alder reactions are in equilibrium, and if you let this reaction stir long enough, eventually it'll go all towards the exo product. So with the Diels-Alder, you need a cis diene. So oftentimes you'll find dienes that aren't locked into position as trans. However, since this is a single bond here, it allows for free rotation. And although the trans is favored, eventually it'll create the cis diene, and then your reaction will be able to occur this way. So here we have our cis dienophile, and then over here I just wanted to show you, if you had a trans dienophile, then you create both trans products, and here you can see that you generate 2 enantiomers. So these are not the same product, so that is one downfall of the Diels-Alder, is that it does create enantiomers. However, we don't have to worry about that. We're using 9-anthracene methanol and N-malamide, and since these are both symmetrical molecules, we're only going to generate 1 product. So the Diels-Alder reaction is a nice reaction because it has atom economy, meaning all the molecules that we're putting in react with each other, and you don't generate any side products. So the only thing that's going to happen is that you're just creating these bonds, and you don't have any byproducts that are just generated waste. They give you an example of an epoxidation using MCPBA, and then so with that reaction you generate benzoic acid, metachlorobenzoic acid, and all that just goes to waste. It has nothing to do with the reaction. So that is a benefit of the Diels-Alder, is that everything you're putting into the reaction generates the product. Also, this reaction is done in water, which is kind of interesting. Neither the compounds are very soluble in water. So what this allows is that the compounds are kind of forced in together, and that allows the reaction to happen much faster than the 3 hours usually required for this reaction. Okay, so we've added the 9-anthracene methanol, 65 milligrams into the 100 mil round bottom, and then 50 mils of water. And then we have it stirring now on a medium heat. With our reflux condenser, always remember water goes uphill with the reflux condenser. And then it's emptying into the sink right there. And now we're going to add in 104 milligrams of the N-methylmalamide. So once that's added in, we can go ahead and put it on the reflux condenser. Make sure you have a tight seal. You can see this kind of came down a little bit. And then we are going to let this stir for 1 hour.
After refluxing for 1 hour, the reaction mixture was cooled to room temperature and then placed into an ice bath. White precipitates have formed, and now we're going to isolate our product by vacuum filtration. We can first pre-wet our filter with a little bit of cold water, turn on our vacuum, and transfer our product over to the Buchner funnel. We can then add some cold water to our reaction flask to rinse out any remaining product. We can leave our product on the vacuum filtration system for several minutes to allow it to fully dry before we submit our sample for NMR using deuterated chloroform as our solvent.